My name is Skye Thompson, and this summer I worked on designing control policies for distributed manipulators. A distributed manipulator is a set of actuators or small robots working together to achieve some kind of manipulation goal. They can be robust and flexible, but designing control policies for distributed manipulation is difficult. A lot of the manipulation tasks these kind of tools perform tend to be non-prehensile, which means these manipulation policies are heavily dependent on both the hardware that you're using and the dynamics of the object that you're trying to manipulate. Specifically this summer, I worked on a novel form of distributed manipulator called a delta array, which is a grid of these delta robots like you see on the left here. What's really cool about the delta array is that it has all the benefits of a more traditional distributed manipulator while also being able to perform tasks like grasping or in-hand rolling thanks to each individual delta's 3 degrees of freedom. But because this is a new tool, we don't know everything about what design factors might be useful to consider when making a delta array or how we can design effective control policies for it. So my goals this summer were to explore what design factors impact the manipulative capacity of a delta array and identify what approaches to control are best suited to it. To start with, I looked at the arrangement of deltas within the array. If you're packing the deltas closely together, they're going to start to collide with each other, which is limiting the effective workspace of each of the individual manipulators. But if you space them too far apart, you're able to get fewer contacts on each individual object you want to manipulate and are risking them falling between the deltas or just out of the reach in general. The ideal delta arrangement is one that maximizes both the effective workspace of each individual delta and the overall density of deltas. We evaluated 3 different kinds of arrangement: square, triangular, and hexagonal packing by simulating deltas in MATLAB. We identified the maximum possible workspace of each delta and simulated a pair of deltas in a given position and orientation going to each of their possible configurations within that workspace. We identified which of those configurations resulted in collisions, and then went back and removed configurations resulting in collisions from the workspace until we had completely separated the 2 workspaces and there would be no more collisions between deltas. This allowed us to estimate what the effective workspace of each delta would look like. Based on these results, we determined that the hexagonal packing was the most effective. It had the least collisions per configuration, which meant that it preserved more of the delta's effective workspace. We also compared this hexagonal packing across different packing densities, so having different distances between the deltas. We found that as the distance increased, the workspace of an individual delta would approach the maximum possible workspace. We found that when attempting to jointly maximize the effective workspace of each delta and the density, having a distance between deltas of between 6 and 9 centimeters produced good results. Using this information, we moved our delta array into simulation. We started our control evaluation looking at a planar translation policy, which is achieved by breaking down the deltas into different groups and having each of those groups execute some portion of a phased gate. So as you can see here, for a hexagonal packing, there are 3 main ways we can break this down, dividing it into 2, 3, or 4 phases. We wanted to compare these and see what the difference between each of these approaches look like when trying to do a planar translation. We found that having more phases resulted in a smoother translation with less vertical deviation and a lower maximum acceleration of the object. But we found another problem. For smaller objects, having more phases means that you have fewer deltas in contact with the object at any given time. So a translation policy that's effective with a 2-phased gate might cause the object to get stuck with a 4-phase gate. In order to further explore this, we tested objects of a variety of different sizes, translating them with each of these phased gates. We found that the trajectory of the translated object tended to stabilize when it had a surface area that was about 8 times the surface area of an individual delta's effective workspace. So as you can see here, we evaluated that based on looking at the z deviation, the max acceleration, and how much it tilted during that translation. Finally, we wanted to look at the trajectory of each individual delta. For all of the tests we performed previously, the deltas were just operating in a simple elliptical trajectory with a phase delay. But we didn't actually know whether this was optimum. So instead, we decided to formulate this as a policy search problem. We represented the trajectory of each individual delta as a sum of weighted Gaussians, which we then used as a prior in performing our policy search. So sampling from this prior, which we used as our elliptical trajectory as our prior, we get a new trajectory, which we can then evaluate on this translation task. We evaluated its performance by measuring the mean velocity and subtracting from it a weighted measure of the maximum acceleration and also the maximum z deviation to incentivize a trajectory that's both fast and smooth. From there, we update our higher level policy, weighting it by as a function of the reward for each of the trajectories that we've tested, and also this other parameter that is a measure of the divergence between the updated policy and the past policy, keeping it from wandering too far away from whatever the previous higher level policy was. What we found was that policies that worked well after running our policy search were policies that tended to be flat during the period of contact compared to the rest of the trajectory, and also that had fewer points during this period of contact, which for our parameterization basically means that the delta moved very quickly during that portion of the trajectory. And you can see that here as we compare our prior with the elliptical trajectory to the trajectory that we learned after 150 rollouts for the biphase gate, which is more stable and also moves more quickly while the deltas are in contact with the object. Based on what we've learned, our next step would be to explore further how learning can inform policy design for this kind of manipulator. Particularly for distributed manipulators, how can we incorporate the idea of all these individual deltas cooperating to learn policies for translation or rotation, or even incorporating more advanced behaviors like being able to use some deltas as a wall, or incorporating 3D manipulations like grasping or flipping. All right, thank you very much.